Hi everyone. In this lesson, I'm going to give a brief introduction to the principles of homogenization. Rocks are heterogeneous materials. Here are two examples of heterogeneous rocks. On the left is a polymictic conglomerate. As you can see that on this scale of observation, the rock is made of many heterogeneous elements, what we have usually called the rheologically distinct elements. On the right is a quartz malonite derived from a quartz vein. Even though the rock is homogeneous compositionally, it is heterogeneous rheologically, because quartz crystals are rheologically anisotropic. Each quartz grain is rheologically distinct from its neighbors because of its unique shape and orientation. Imagine a heterogeneous material like this is subjected to deformation. The stress and the strain in each element will be different. If we use sigma alpha to stand for the average stress and epsilon alpha the average strain or strain rate in that element, then the stress and the strain relationship in the alphath element can be represented by this relationship if the material is linearly elastic. In that case, C is the elastic stiffness. If the material is linearly viscous, then C is the viscous stiffness. The relationship in each element can also be written in the reverse relationship using elastic compliance or viscous compliance. These two relationships are equivalent. Now, let us say that this is a representative volume element of the rock. The volume-weighted average stress on the representative volume element scale is this one. The volume-weighted average of the strain or strain rate is this one. Now we wonder how the average stress on the representative volume scale is related to the average strain on the same scale. That is, what is the overall effective behavior? And the C bar here represents the effective stiffness. And M bar similarly stands for the effective compliance of the material on the representative volume element scale. So homogenization in micromechanics means methods or procedures to get effective rheological properties of a heterogeneous material from rheological properties of the constituent phases. We can now state homogenization more rigorously. Given a heterogeneous material on the scale of a representative volume element, the material is heterogeneous. It's made of a matrix, the C0 phase, and many inhomogeneities, or commonly we call rheologically distinct elements, RDEs. C0 for the stiffness of the matrix, and C1, C2, etc. stand for the stiffness of inhomogeneities. Lowercase c here stands for the volume fraction of that element, so C0 stands for the volume fraction of the matrix phase. If the material doesn't have a connected matrix, then it's a polycrystal or polyelement material. In that case, the different phases are C1, C2, C3, etc. There's no C0 phase, there's no matrix phase. So homogenization really is to look for a hypothetic effective medium. It is homogeneous on the representative volume element scale, and it has a stiffness C bar, that is the effective stiffness. The volume fractions of all the elements must add up to 1. The average strain on the representative volume element scale is represented by this chevron bracket, which means the volume-weighted average. The same is true for the average stress on the representative volume element scale. The rheological properties of the kth phase is represented by this rheological equation. Stress is related to the strain or strain rate by the stiffness, specifically for that phase. Now homogenization is the effort to find the overall stiffness or overall compliance for the material on the scale of the representative volume element. How do we get the effective stiffness? That's the motivation of homogenization. Simplistically, we can think of the volume-weighted average of all the constituent stiffnesses, or chevron average of all the constituent compliances. The first average is what is called the Voigt average, and the second average is the Roy's average. Think of a simple situation, a two-phase material, starting with a uniform matrix with a viscosity eta 0. Now let's imagine what happens if we add a second phase. The second phase has a distinct viscosity eta 1, and suppose the viscosity ratio is constant R. The effective viscosity of this material as we increase the content of the second phase. Now the simple situation is we can consider the Voigt average. So take the situation of the viscosity ratio of 20. At concentration of 0 of the second phase, the effective viscosity divided by the strong phase is 1/20th. So at concentration 0, it's 0.05. As we increase the concentration of the second phase, the Voigt average increases linearly. So the effective viscosity increases linearly as we increase the amount of the strong phase. If we use the Roy's average, the effective viscosity goes up along this green curve. So as you can see that the two averages are far apart. Voigt average gives the upper bound, and the Roy's average gives the low bound. The two bounds are really far apart. If the second phase is rigid particles, Einstein got the result that the effective viscosity is related to matrix viscosity by this relationship, as long as the second phase is very direct, so C is very small. This relationship was also obtained by Jeffrey. See the problem with this simplistic Voigt average and Roy's average? They only gives the upper and low bounds, and the two bounds are far apart. And also, they do not consider the microstructures of inhomogeneities. So the second phase may have different shapes, different orientations. The second phase may also have a preferred orientation, and that is not considered in this simplistic average. So we need a more rigorous way to do the homogenization, and that is achievable with the partitioning equations from micromechanics. These two partitioning equations will be essential in the exercise of homogenization. Of course, this relationship was obtained based on the assumption that the RDE is a single ellipsoid enclosed within an infinite uniform matrix. How do we apply that to a finite representative volume element size needs to be justified, and more justification will be given in the next lesson. For now, I can state that as long as the inhomogeneity is small compared to the representative volume element, then the RDE can be regarded as a single element in an infinite matrix. There are other assumptions that these partitioning equations was obtained, of course. Details how these partitioning equations can be applied to more realistic materials will be discussed in the next lesson, but in this lesson, let us assume that these partitioning equations apply, and our homogenization is based on the fact that the material is linear. Now, the general principles of homogenization can be illustrated here. So we are dealing with a heterogeneous material, either a material with many inhomogeneities embedded in a common matrix phase, or the material is a polycrystal or polyelement continuum. Homogenization can be done either on a strand boundary conditioning on the representative volume element, in which case we use the strand partitioning tensor, or based on the average stress on the representative volume element, in which case we use the stress partitioning tensor. Either way, their homogenization principles are similar, and I will use the strand partitioning tensor to illustrate the general principles here. So to reiterate, the average strand is this one. Volume-weighted average of the strands or strand rates of all the constituent elements. We can write the strand or strand rate of each element in terms of a partitioning relationship. This partitioning is written in terms of the average strand on the representative volume element scale, and that is called the global partitioning relationship. If we expand the first relationship, then we get this. And that equation with this partitioning equation submitted into this term gives rise to this equation. On the other hand, the average stress is this one. Submitting the Hooke's law, we get this relationship. And submitting this into this relationship, or combining these two equations, we get this relationship. Now compare these two relations. So we immediately found that the effective stiffness is this package. That is, we got an expression for the effective stiffness of the material as a function of the properties of constituents. The only unknowns here are the strand partitioning tensors for all the elements AKs. So depending on how we compute these AK terms, we have different homogenization methods. Before we get to those methods, we need to distinguish global and local partitioning. So the partitioning we have just written is the strand or strand rate of the kth element as a partitioning relationship of the average strand. AK is called the global strand or strand rate partitioning tensor. We can alternatively write the strand or strand rate in the kth element as a partitioning relationship like this in terms of the average strand or strand rate of the matrix. And this GK is called the local strand or strand rate partitioning tensor. Now remember this relationship we get in the last slide. Submit this local partitioning relationship into this term. We get to this and eventually this relationship. This allows us to get an expression for the average strand or strand rate in the matrix phase. Now submit this into this relation, we get this relationship. Now compare this relation, the first equation, and the equation we just obtained. The global partitioning tensor and the local partitioning tensor are related by this relationship. Now we already have this general expression for the effective stiffness. All we need to do is to compute the global strand or strand rate partitioning tensor for all the constituent elements. Homogenization methods differ in how AK are computed and the medium selected for the computation. In the Eshelby method, the inhomogeneities are so direct, the medium is just the matrix. The global and the local partitioning tensors are the same. In the so-called Mori-Tanaka method, the medium is still the matrix, but the local strand partitioning tensor is first calculated and is used for the calculation of the global strand or strand rate partitioning tensors. There are materials that do not have a matrix phase, and these materials are called polycrystal materials or polyelement materials. For these materials, self-consistent method is used for homogenization. The effective stiffness is used for the calculation of the Eshelby tensors and the strand rate partitioning tensors. Because of this, self-consistent method leads to implicit equations, and the self-consistent equations must be solved iteratively in order to get the homogenized stiffness. I am now going to use a very simple material as an example to illustrate the homogenization calculation. Let us consider a biphase material made of two isotropic phases with viscosities eta 0 and eta 1. The viscosity ratio is R. We have this general expression for the effective stiffness. If there is a matrix phase, this is the expression, and if the material is a polyphase or polyelement material, this is the expression. Now let us assume that the phases are all spherical and isotropic. In chapter 10 of the lecture notes, it is shown that for spherical inhomogeneities in isotropic incompressible materials, the Eshelby tensors are very simple. The Eshelby tensor is this relationship. JD is the fourth order deviatoric identity tensor. Again, for details, please read the lecture notes. For such simple materials, these effective stiffness expressions are reduced to an effective viscosity expression. The expressions are scalar equations. The effective viscosity is related to the viscosities of the two phases and related strand partitioning tensors. Because the Eshelby tensors are very simple, using the expressions of the last slide, it is easy to show that the strand rate partitioning tensor for the eta 1 phase in the Eshelby method is this relationship. It reduces to a scalar. For the Mori-Tanaka method, the relevant strand rate partitioning tensor is also reduced to a scalar. In the situation, the two phases form a polycrystal aggregate. The strand rate partitioning tensors for the two phases are also reduced to scalars. Now in the end, the Eshelby method leads to this relationship. So the effective viscosity normalized against eta 0 phase is related to the viscosity ratio and the concentration of the eta 1 phase by this relationship. The effective viscosity using the Mori-Tanaka method is this one. And using the self-consistent method, the effective viscosity is given by this implicit equation which can be solved. So here is a plot for the situation. The viscosity ratio is 20. The Vogt upper bound is here and the Roy's lower bound is here. The Eshelby result is applicable only for very dilute situations, for C very, very small. Now, if the second phase is rigid and it's very dilute, the Weyermann-Einstein relationship is this. So this quantity is related to the concentration of the rigid particles as long as the rigid particles is very dilute. Taylor obtained this relationship. All the above results converge to this simple relationship as long as C is very, very small. So for dilute situations, all the results converge to this. For more general situations, such as polyphase material, or if the inhomogeneities are ellipsoidal, or if the material is anisotropic, it becomes not possible to get the homogenized stiffness by using these simple analytical results. Numerical computation must be adopted. However, the principles are the same. The simple exercise of two-phase materials gives us a lot of insights for the rheological weakening during monazitization. When a rock, like a granite, before its monazitization, the textures are polycrystal. Quartz, feldspar, and other constituents, they form a polycrystal. So the more appropriate way to get the effective viscosity is to use self-consistent homogenization. And the self-consistent homogenization gives the effective stiffness like this. It's below Vogt, but it's far above Roy's. Now the same material, when it's monazitized, there is a connected matrix phase made of dynamically crystallized quartz, mica, etc. The material becomes much weaker. Mori-Tanaka method becomes more relevant. Many decades ago, Mark Handy proposed that there is a transition in behavior from uniform strain-like to uniform stress-like as the strain localizes. So in the uniform strain case, the behavior is strong. In the uniform stress model, the behavior is like the Roy's average. We can update that understanding as strain increases, such as in the process of malonatization, there is a transition from a polycrystal behavior to a behavior that is like Mori-Tanaka behavior. There is a transition from self-consistent polycrystal behavior to Mori-Tanaka behavior during malonatization. I will address nonlinear rheology and other issues related to the more general application of micromechanics in the next session. So that's it for this lesson. Thank you for your attention.